Hi, welcome to AB Video 3.4b, Part 2, more on relative extrema and points of inflection. To be 0. Okay, this is asking you on a calculator. Find the first and second derivatives of the function. Find any relative extrema and points of inflection. We're assuming they're talking about doing that visually. And then graph f prime and f double prime on the same set of coordinate axes and state the relationship between the behavior of f and the signs of f prime and f double prime. So here's a very ugly function, thank goodness, and we don't have to do it by hand. And they're telling us that we're only looking at this function for x between negative root 6 and root 6. Okay, so if you enter f1 of x as x squared square root of 6 minus x squared, then your derivative function would be d dx of your f1 of x, and your second derivative function would be d squared dx squared of f1 of x. So you never have to really find them. You can graph them without finding them. Or you could find them and then copy paste them in, whatever works for you. Okay, that would be fine. So this is me actually doing that work, but you wouldn't need that. Okay, so here's how it looks. The graph of just y1, which is your original f of x, on the window from negative root 6 to root 6 would look like this. Now you can visually see that this graph has a max here, and you could use a calculator to find that max at negative 5.657. Here's another relative max at 2, 5.657. You'll notice there's a min at 0, 0. You'll notice there appears to be 2 points of inflection, and your calculator can find those as well. Okay? If you look at all three graphs together, what you will notice, let me just look at f, which is the red graph, and f prime, which is the green graph. You'll notice that whenever f prime is positive, i.e. above the x-axis, f is increasing. As soon as f prime is negative, f is decreasing. F prime is positive again, so f is increasing again, and f prime is negative from here to here, hence f is decreasing. Okay, number 58, consider a function f such that f prime is decreasing. Sketch graphs for f if a, f prime is negative, and b, f prime is positive. Now you're going to have to think a little outside the box on this one. If f, remember, we know when f decreases, we know that that implies that f prime is negative. So if we go one level further, when f prime decreases, that's going to mean the second derivative is negative. And of course, we know the second derivative is negative, means the graph is concave down. If we combine that with part A, where f prime is negative, which means f is decreasing, you have to graph a graph that is both decreasing and concave down. So here would be an example. For part B, instead of f prime being negative, f prime is positive, so f has to be increasing. This time you have to graph something that is increasing and concave down. So any graph that's increasing and concave down will do. Here they're going to ask you, they're going to give you the graph of f, and based on that graph, you're going to come up with the graph of f prime, f double prime, and they're not going to give you the equation. So you got to start looking at things here. First of all, you have a relative min at 1, negative 1. You can see that our function f, you can't say the function or it's f is increasing from 1 to infinity. F is decreasing from negative infinity to 1. You can see that f has a horizontal tangent line at x equals 1. Well, that means f prime of 1 is 0. And you can see that f is concave up the whole time. Well, what are the conclusions for f prime in this case? The conclusions for f prime are that if f is increasing, f prime is positive in that interval. If f is decreasing, f prime is negative. If f prime of 1 equals 0, then the graph of f prime has the point 1, 0 on it. If f double prime is positive, remember when the derivative of a function is positive, that function is increasing. So what we have for f prime is we know that to the right of 1, f prime is positive, so I blocked off all the negatives. F prime is negative to the left of 1, so I blocked off all the positive. F prime has the point 1, 0 on it, and then we know that f prime is increasing the whole time. And then finally, based on that graph, we can come up with the graph of f double prime. Oh, for goodness sake. Okay, so for f double prime, we have that, and I mean this, actually I'm going to do this one very simply. Doesn't this look like a parabola, which means its derivative would be a line, which means the derivative would be the slope of that line. But we can establish that since f prime is increasing the whole time, that means f double prime is positive the whole time, so I block these off. Okay, here's another one. Again, here's the graph of f. F prime of 2, as you can see, doesn't exist. F is increasing on the left side of 2, decreasing on the right side of 2. F prime never equals 0. F is concave up on both sides of 2 and concave down nowhere. So the conclusions for that, if f is increasing somewhere, f prime is positive, so there's no negatives. If f is decreasing, f prime is negative, so there's no positives. F prime never has an x-intercept because f prime is never equal to 0. And f is concave up the whole time means that f prime, let me get rid of this, means that f double prime is positive the whole time, which means f prime is increasing the whole time. And of course f prime, f double prime is never negative, which means f prime is never decreasing. So we just kind of fill in the blanks. Over here, you can see that f prime is increasing the whole time, which means f double prime is positive the whole time. We're assuming that this is probably a vertical asymptote, same thing. I mean, and we know it is, but probably the same thing will happen here and here. And then we have that f prime is concave up, which means f triple prime is positive, which means f double prime is increasing. And f prime is concave down, which means f triple prime is negative, which means f double prime is decreasing. And here's kind of the same idea. You're just kind of fitting everything together. They give you f of 0 equals f of 2 equals 0. Those are points on your graph. First derivative is negative to the left of 1, which means f is decreasing to the left of 1. F prime of 1 equals 0 means you have a horizontal tangent line at x equals 0, which means x is a critical number. Could be a max, min, or a point of inflection. The first derivative is positive to the right of 0, which means f is increasing to the right of 0. I mean, to the right of 1. And now is when you can make a decision. If it's decreasing on the left of 1 and increasing on the right of 1, it's got to have a relative min there. Second derivative is positive everywhere, means f is concave up everywhere. So any one of these graphs would suffice. They all go through the point 0, 2. They're all concave up everywhere. They're all decreasing on the left of 1 and increasing on the right of 1 and have a relative min at 1. And this is a tricky question from the AP. Find A, B, C, and D so that this function has a relative max at this point, relative min at this point, and a point of inflection. Well, here's what happens. If there's a max at 2, that means f prime of 2 equals 0. Can't be undefined because it's a polynomial. All the derivatives are polynomials. If there's a min at x equals 4, f prime of 4 is 0. If there's a point of inflection at 3, 3, then f double prime of 3 has to be 0. Again, the second derivative will never not exist. So I find the first derivative. I plug in the fact that if I replace all the x's by 2 in the first derivative, I get 0. If I replace all the x's by 4 in the first derivative, I get 0. So I get these two equations. And if I take the second derivative, which is this, if I replace all the x's by 3, I get 0, which gives me this green equation. You now have 3 equations and 3 variables. It's basically a process of solving the system of equations. Okay? Now, what happens is when you get to this point, you'll be like, oh no, I don't have enough information. But the thing to keep in mind is that if the point 24 up here, you're told is a relative max point, that means that point is on the actual function. So you now know f of 2 is 4, so you take f of x, replace all the x's by 2 and the y's by 4. And you'll get this very ugly system of equations. Feel free to use your calculator to solve that. Easy max min word problems, they give you the equation. Notice they say what order size will produce a minimum cost. We're trying to minimize the value of c, which is our function. So what do? We find the domain. X can't be 0, but of course x is the number of units ordered, so it can't be negative. It has to be positive. Rewrite the original function, find the derivative, find the critical numbers, and of course our domain is x is bigger than 0. We get one critical number, put it on the number line, blah, 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 blah. Same old for uh, relative extrema, first derivative test for relative extrema. And then the minimum number of units ordered would be this, and the minimum cost would be that. And finally, this is just something that we're adding on. With the AP, they used to let you just use this number line like I've been doing, and then you could just say there's a relative max here and a relative min there. The AP is now requiring that you actually write out a sentence that says f has a relative max at x equals 1 because, and then it's your choice, because the first derivative is positive on the left of 1, negative on the right, or because f is increasing on the left and decreasing on the right. And same thing with point of inflection, because the second derivative is positive on one side, negative on the other, or concave. And that's the end. Whoops. And that's the end of video 3.4b, part 2.